Okay, so just to share with everyone, I will try to do a grade update today. And I want to go over a little piece of the notes from a definition and then do an example, and then we're going to start using the rules for sums.
Hello, Cassandra.
Hello, good morning. Okay, so first part I want to put back on the board is the integral from a to b of f of x dx. Is the limit as n goes to infinity. I'm going to go ahead and go with, so you would, we're going to go with the general form. You have your sum from I equals 1 to n of f of x sub I star times delta x. Okay, but then when we just focus on using right-hand endpoints, we don't need the star, and we know what the x sub I numbers look like. They look like this. Okay, like that, actually. Okay. All right, that looks a little better. Okay. And the limit would be it's the limit as n goes to infinity of the sum. Your integral a to b of f of x dx is just like this. You don't need a star. So maybe the limit as n goes to infinity from I equals 1 to n of f of x sub I, and this is your x sub I, and then times delta x. And just recall, delta x is b minus a divided by n. Okay, and really it's like the area under the function f from a to b to the x-axis, under your function to the x-axis between a and b. Okay, we're gonna do this example. Where we're approximating an integral from 1 to 5. The function.
By the way, there's 2 weeks left in the semester, right?
Well, I can check my calendar in a second, but we're almost at the end of the semester. Yeah, I'll check in a sec. Okay, so integral from 1 to 5 of x squared and times e to a negative x. Okay, we're gonna get that using right endpoints and n equal to 2. Okay, so on the sign, we're in week 13 out of 16 weeks of school, with the 16th week being finals. So we're getting through this week, and then there's next week and the last week of instruction after that, where we're going to do review. And we're going to do a take-home test for the final. So I'll have your test, and then you'll turn it in by the 20th of May. That's the last day. Yeah, I know, it's crazy. But I'm glad that we made it to chapter 5. We're doing great, actually. So I am proud of us. I still need to make more homework in your final, but we did good.
Wait, is chapter 5 like the last chapter for the semester or not?
It's sort of the last chapter we want to reach for Calc 1. We want to make it to 5.5.
Yeah.
And then if we do make it through those
What
notes.
did you intend to go to, by the way? What did you intend to like end the semester on, like what chapter?
5.5.
Okay.
Yeah.
We're pretty close. Don't worry.
We're close. Yeah, we're almost to 5.2. So. All right. And it's going to get kind of easier and easier, less tedious, like this kind of problem, all this as we keep going. But for now, we're going to get this integral with this definition. And again, just like approximating the area under this function from 1 to 5, from this function to the x-axis between those bounds. All right. Okay, first thing I looked for was delta x. So 5 subtract 1, divide by 2. Okay. And I think the next thing I looked for was my x sub I values. X sub I with the right side. Is a plus, I'm going to write it down, a plus I times delta x. A is that place where you start 1. And then plus I times 2, or plus 2i. I think, well, I might be overdoing this. Let me see. Delta x. Well, I kind of want this correct, but it's a little bit much. So we can actually just draw a sketch, and we're going from 1 to 5. And we're getting the area with, we're approximating this area with the area of 2 rectangles. So we're going to have let's see, from I equals 1, so 1 over 3. And then the next interval goes from here, with the right end being at the place where I is equal to 2, x of 2 would be 5. Okay, we're putting in 3 for the first right end, and then 5 for the other. Okay, so the integral is approximately equal to. So actually we're not, I didn't do a limit, I just did the rectangles. So the sum of the approximating rectangles using right endpoints was r sub n or r sub 2. And that would be delta x times f of 3 plus this with delta x times f of 5, wherever that goes. Okay, so delta x was 2. And then put 3 into your function, so 3 squared would be 9. And then e with the power of negative 3. Add 2 times f of 5, so it's going to have a 5 squared is 25. And e to the power negative 5. Okay, so I just wrote this as 18 over e cubed. Okay, add 50 over e to the 5th. And left it like that. Okay, and then in the notes are the rules of sums, and after that we can do more examples. Let's see. Okay, like this one. We're going to find the integral from 0 to 3 of 25 minus x squared dx.
Where do you get the e's from for the last example?
For the part of the function with e to the power negative x.
Oh, okay. Okay, I see. Oh, I see, I see. And that's fx, right? That equation?
Yeah, this whole part.
Okay.
We're gonna put maybe like brackets. So first I found delta x.
Wait, isn't dx the same thing as triangle x?
Sorry, did you say
Because
E?
because there's dx up there, and then
Oh
I
yeah,
just realized that. Wait, dx? Where did dx go? Wait, or am I just overthinking myself? Oh, my bad.
no, I think it's okay. I can peek at a book in a second, but I'm pretty they might mean the same thing. I'll check in a book. It's just like a notation thing. But yeah, delta x dx might be the same. Change in x. Okay. I'll look in just a moment. I just want to at least find this little delta x for this problem, and then we can see what the book says. Okay, 3 minus 0 over n. So 3 over n. Actually, I think we sort of did part of this problem before, and I just want to finish it now that we have all the rules. So I might skip some steps, but we'll come back to this. So let me look in the book really fast. Okay, getting closer. So in the book, this book says that delta x is to represent a change, either a change in x or a change in y. So I might do a little bit more looking later just to see like what might be on Google, but I just to kind of like get a better understanding of what this represents, which if we have time at the end of class, maybe I'll just look in the book again in this section. Okay, for now, I want to get my x sub i's and then set up the limit, and then we're going to hopefully find like the limit. Okay. So x sub i's look like a plus I times delta x when you use right endpoints. A is the starting place, 0. Just copy that I, and we just got delta x, 3 over n. Okay. The integral from 0 to 3 of 25 minus x squared dx. Is equal to
What
the
happens to
limit.
the end, by the way?
Huh?
What happened to the end? I mean the n. Why is there no like variable for the n?
like in the integral.
N, like why is it just N? No, like N. Why is it just like 3N? Does N equal nothing or
N,
N?
yeah, N represents how many rectangles you're using to approximate the area. And then we're going to let N go to infinity so that we're filling up the area with infinitely many rectangles. And then width is going to get smaller and smaller and smaller.
Oh, so we're just gonna leave N like that. Okay.
Yeah.
Yeah, and so yeah, because I think like in the last example you placed N with something, right? Or
Yeah, last time we had N equal to 2. And then you can have N be like 3, 5, bigger and bigger numbers, and then you're getting smaller and smaller rectangles, but you're getting better approximations of the area. So we're actually going to let N, so that's why we have this limit. And you let N go to infinity. So like as this gets bigger and bigger, the overall value is going to 0, it's getting smaller and smaller. So this delta x, the width of the rectangle, gets smaller and smaller. And then I'm going to draw a quick sketch. Okay, so like last time we talked about having n equal to 2, so 2 rectangles where you just break this in half and make a rectangle here and here. And you get a kind of good idea of the area, but let's say your n is 4, so 4 rectangles. So we'll erase. We'll split this up 4 white into fourths, and then have 4 rectangles in this one. Okay, and you want to increase n. So like say n is like 8. So just cut all of these up. So anyway, n is the number of rectangles that you're making. And the way is like representing the way that you're going to take that interval and make it into little sub-intervals. All right, let's go into the limit of the sum from I equals 1 to infinity, or sorry, 1 to n. Okay. We're gonna just put the general like definition of f of x sub I times delta x. Okay, but then put in delta x, it's 3i over n. Oh, it's just 3 over n. And then we're going to put in our x sub i's, this value. And again, I think we sort of worked on a problem like this last class, so I'm going to probably, like after we plug in this input to that function, we'll kind of like jump past the part where we then distribute this 3 over n. So anyway, we've got this limit, n going to infinity of the sum from I equals 1 to n of 25 minus 3i over n squared times the 3 over n. we distributed a 3 over n. We got that 75 over n, and this was 27i squared over n squared. Or sorry, it'll be over n cubed. So here. And then if a value is affected by the index, then it needs to stay in the sum. Otherwise, you can bring that value out. So that's what we're going to do to sort of set up these sums so that we can kind of find their values. All right, so here the 75 is the number. I'm going to bring it out in front of the sum. That n is just some variable, but it's not affected by this indexing. So I could bring n 1 over n out of the sum like this. So this is over here, and then multiply with the sum from I equals 1 to n of 1. Same with this, like, okay, there's two things going on. One is I don't have enough space to write all of this down. So I need to kind of like erase over here and get this all going. But also, I think before we do this part, I want to take this and have the sum on that term, and then also the sum on that term, and then like manipulate each sum. Okay, so from here, I'm gonna go down here. This way. From here to here. Limit as n goes to infinity. The sum from I equals 1 to n of 75 over n. Minus the sum from I equals 1 to n of 27i squared over n cubed. Okay, now for this sum, we're going to bring 75 over n to the front and then leave 1 like, in the sum. And I need to bring the 27 over n cubed to the front, but that I squared has to stay because it's influenced by that index right there. So this sum, we're going to use the first rule for, and we'll have 1 times n, or n, multiplied with this 75 over n. And then I'll look up
Wait,
this.
Professor?
Yeah.
Does it for the first equation is just 1 because there's no I anywhere, or is it just because like there's no I? Okay.
Yeah.
So like if there's no I in one equation, then it just equals 1, right?
And pretty much then, well, you have all the other values multiplied with it, but then, yeah, then you're taking the sum of 1 and there's no i's. So yeah, like this is just 1, but then I'm just kind of pointing out that there's also that number right there that you're multiplying with. Okay, let's write down that first rule. So we're going from here to here, rule number 1. We have the limit as n goes to infinity. Of 75 over n. Okay, and there's this sum from n equals 1 to n of I squared that we're going to replace. And you take negative 27 over n cubed. And then here, this is going to be n times n plus 1 times 2n plus 1 over 6. Okay, let me see. So in the notes from here to here, that's rule number 5. And then the other rule for sums we used was rule number 1 right there. Okay, and it just kind of worked out. Trying to simplify this part here, that part there. Okay. The limit as n goes to infinity of 75. Minus 27 is 3 times 9. And that 3 with a 3 from there would reduce. So I think you'd have a 9 over 2. Let me go sneak peek. Okay, we're going to have that n right there reduced with one of these n's in the denominator, which would leave n squared in the denominator. And then we're going to work out n plus 1 times 2n plus 1. So we'll FOIL that. Okay, so we're subtracting from 75. 9 over 2n squared times d. 2n cubed, oh no, 2n squared. Plus n plus 2n, so it should be plus 3n.
Professor, where did you get the n and n plus 1 and 2n plus 1 from, by the way?
Yeah, the
Where'd you get like n and where'd you get that from?
that is a rule for sums. It's rule number 5, which I can write down. It's like the sum from I equals 1 to n of I squared. And then I'm just going to double check that I use the right one. N times n plus 1.
Hey, Cassie.
Yeah.
I'm just okay. So I'm a little bit confused on like the 6 in the denominator. Where did that 6 come from?
So it's
It's like
this 2
it's the one, yeah, you just erased.
over 6. So this is the rule. The sum from I equals 1 to n of I squared is always equal to n times n plus 1 times 2n plus 1 over 6.
Over 6. Oh, okay, I see.
Okay. And then while we're here, so like there's this one is always going to happen every time, like every time the sum from I equals 1 to n of I squared is always equal to this. N times n plus 1 times 2n plus 1 divided by 6. The other one I used was the sum from I equals 1 to n of 1 would be, you take the number and times n, 1 times n, or n. Okay. I hope that helps. Any other questions though?
Yep. Thanks, Cassie.
Okay, cool. Alrighty, we foiled this out. We got this there. I think we want to distribute the 9, create separate terms, and then we're pretty much done. Okay, let's just do this first. 18n squared. Add 37n, 27n plus 9 over 2n squared. Okay, cool. And again, I want to break this up with 18n squared over the 2n squared, and then the 27n over that, 9 over that. Oh. We don't need the sum. We took care of all that. So yeah, it's just a 75 right now. And this would be a -9. Okay. Minus, I guess it's 27 over n. And minus 9 over 2n squared. Okay. Okay, so as n goes to infinity, this value goes to 0. Same here. This n in the denominator will make this whole value go to 0, and we'll end up with 75 minus 9. A 66.
By the way, Cassie, is this online?
What was that?
Is this online?
Yeah, it's definitely posted, but I just noticed that I have a small typo. I forgot to like distribute the minus sign. So I'm gonna like rescan the notes tomorrow. Just like fix that part. And we've got 5 more minutes, so I think I'm going to introduce this theorem, and then we'll get back to notes tomorrow. And hopefully I'll have your grades updated in your tests for you. Okay, let's see. We got 2. Just pretty much just restating the same things that I've been going over and over again. But I just want to make sure I write. I've been saying the integral of, and I just want to make make that word and also the word integrable clear. So a function is integrable or like you can find the integral of that function on an interval. Oh. Okay. This is not a definition. This is a theorem. So we're going to back up. And then it says if a function is integrable, then I'm pretty sure what they're trying to say is then that limit does exist and you can find the integral. So you can integrate from a to b of find the integral of your function from a to b. by getting the value of the limit. So I'm pretty sure where they're going with this is to say, like, if your function is integrable, then it means that this limit does exist, and you can like find its value and maybe using those rules for sums. And we're out of time. Okay, so again, just kind of introducing this integrable, or this is called an integral, or we can integrate this function when that limit does exist. Okay, thank you, everybody. Definitely big thanks to the people who came to